Welcome to another video for Stat 212. In this video, we're going to be getting into hypothesis testing, which is an important part of the inferential process. So we've talked about confidence intervals before this point, and how with confidence intervals, what we do is we take our sample statistic that we hope is a reasonable estimate of a parameter. We make an interval around it, and we can say that we are X% confident that the true parameter should be in this interval. And we base the width of that interval based on how wide the sampling distribution for that sample statistic should be. So based on the information we have, we can kind of construct how wide the sampling distribution should be for the mean or the true proportion or something like that. And thus we know that 95% of the time we should be within, about this much distance of the true parameter from either side. So we're going to kind of use the same ideas with hypothesis testing. We're just going to ask this question a slightly different way. So instead of starting with our sample statistic and trying to provide an estimated range for where that parameter could reasonably be, we are actually going to start with a hypothesized parameter value that we're going to call the null hypothesis. And then we're going to make a judgment about how likely we are to get the sample result we did if this candidate parameter really is the parameter. And if we're kind of in a reasonable probability range, that if the sample result that we saw is something that we could reasonably get by random chance if it's true, then we're going to, what we say, fail to reject the null hypothesis. We're going to say that this candidate parameter is a candidate parameter. It makes sense that it could be true, that the sample result we got is something that we would reasonably see if it were true. But if our probability of likelihood's really low, meaning that the sample result we got is really unlikely to happen by random chance if this really is the candidate parameter over here, when that happens, we're going to reject the null hypothesis. We're going to say that the results that we saw don't make a lot of sense if this value really is the parameter. Therefore, the parameter is probably some different value. Okay. So we're going to look at this with this example that you hopefully saw on the previous video, and that is with my friend Milena trying to guess the color of a card without seeing it or without it being revealed. So as you know, with regular cards, they can be red or black. So she was guessing with 50% probability if she was guessing by random chance. However, we're curious if maybe she had some advantage. So we're going to kind of put that parameter to the test. So our candidate parameter here is that she's guessing with random chance 50%, and we're going to judge how likely or how reasonable this particular sample result is under that null hypothesis. So she guessed correctly on 9 out of 12. Now, this first question is kind of for you here. Is this sufficient evidence that, in this case, well, it's not a student, it's Milena, has some advantage, and how might you make that determination? So what do you think? Do you think that she had some advantage here, or do you think this result that we saw is something that could happen by random chance? All right. You can pause if you'd like to think about it a little bit more. But really the root of the question we're trying to get to is if she was guessing by random chance, how likely, how often would we see someone guess at least 9 out of 12 correctly? This is the question that we can answer, and we can use probability here to determine that. So the question can be addressed by thinking, maybe I should say, I'm not going to say thinking, I'm going to say calculating. How likely we are to see at least 9 out of 12 guess correctly if P, and this is the proportion, if the true proportion that she had to guess it correctly is 50%. So not p-value, which we will talk about a little bit later. So I'll try to write p-value when I mean a p-value, and I'll usually just write p if I'm talking about like a proportion, like a parameter in a population. So in this case, our hypothesized proportion is that she's guessing with 50% chance on each card. Okay. So this is an inferential question, right? We have a sample of data of her guessing that is hopefully representative of what would happen over time if she was continuously guessing these card colors. And so we're trying to determine, is this person guessing, based on the 9 out of 12 that we saw, is that indicative of some kind of advantage? Or again, is this something that we could see by random chance if somebody was guessing with 50% probability? So it's kind of our two possibilities here. Oops, sorry about that. Our two possibilities here is that she's either guessing by random chance, or that she has some kind of advantage that is different than 50% here. All right, so what we can do here is we can represent the probabilities of each of these possibilities of getting different numbers of cards correctly under the assumption of 50% guessing. And so this is going to be something called a binomial distribution, which we have not learned in this class, and we're not really going to use anywhere else in this class. I'm just going to kind of mention it here in so much that it's helpful for this particular question. But you don't necessarily need to understand the binomial distribution or use it for calculations anywhere else. But the binomial distribution is basically a probabilistic method for understanding how likely we are to see a certain number of successes out of a total, given that there is a probability of success for each trial. So in this case, we're looking for how often we see 9, 10, 11, or 12 successes out of 12, given a probability of success of 0.5. So again, we're looking, now in this case, what I do want to clarify is that we're not just interested in the probability of guessing exactly 9, because we have to think big picture what's going on here. Really what we're interested in is how often we do this well or better, how often we are this far or farther away from this null hypothesized parameter of 50%. So that's why we're going to actually calculate this whole range right here. So how often we're getting 9 or above, because, right, so if she had guessed 10 correctly, that's also unusual. And so we kind of want to lump that into the same category of results of how often are we getting 9 or better, because that's how unusual our particular result was. Now, what I'm going to do is I'm going to use R to calculate this, and I'm going to use a command here that we have not learned and we're not going to be using otherwise. But I'm going to be using the binom family functions here. So it's kind of like p-norm. So remember how we had p-norm for calculating normal or probabilities related to the normal distribution. We can use p-binom to calculate probabilities related to the binomial distribution. D-binom would be very specific ones. So this is like the particular bar at 9 successes, the probability of getting exactly 10 out of 12, 11 out of 12, or 12 out of 12. So if I add these all together, this is going to represent my probability here, which is going to be 7.3% approximately. I'm kind of in the way there, so you can't really see this, but there we go. So I'm going to go over here. Oops, that's too far. So apparently about 7.3% of the time, we are getting at least 9 or more successes out of 12, given a probability of success of 50% per trial. We could also use p-binom, but it's a little bit confusing because since this is a discrete variable, if I start at 9, it doesn't include it, so I have to start at 8, but I will get, again, the same result. So it does the same thing, just in a different way. All right, so let me switch back to the notes. There we go. All right. So we calculated here that we're going to land over here about 7.3% of the time. Okay. So again, that's kind of a call here, right? Is that unusual? Like, does that mean we have evidence that she had an advantage based on that probability? Or does that mean that this is kind of something that could happen by random chance? That, if she's guessing with 50% chance, we'd see this 7.3% of the time. So no one's going to be able to really tell you that because it's context that dictates this and how confident we want to be. But I think our intuition is going to tell us that this is a somewhat unusual result, right? This is not going to happen very often. 7.3% of the time is like 1 out of 15. 1 out of 15 times we would see something as unusual as this by random chance. So I'd have to take 15 people, have them guessing at random, and I'd only expect about one of them to get 9 or more cards correct by random chance. So it lends the suggestion that she had an advantage, and she did. Which, if you didn't know or didn't guess by now, those were trick playing cards. So she was playing along. So we totally orchestrated that she'd get exactly 9 out of 12 just for fun. We did not take 15 takes until we got to 9 by random chance. So she just kind of read the card because it had a little symbol or whatever on it to tell you what kind of card it was. But by the probability, right? So again, if we're just judging by the probability, suggests this is pretty unusual. To happen by random chance. Not impossible, of course. I mean, like I said, about 1 out of 15 times, this is probably going to happen by random chance. So it's not impossible, but it is kind of improbable. We could definitely say that here. All right, so that was a case where we had not very many categories, right? So we're talking about counting cards out of 12. However, in general, when we're working with measurable data or just data where we have a lot more possibilities, we can actually just approximate to the normal distribution how often we would see different responses here. So let's look at an example here where we're looking at 100 coin flips, and we observe that 56 of those coin flips came up heads, 44 came up tails. Does that mean, is there any evidence that maybe the coin is not fair? Or is this a result that I would expect to happen by random chance with a fair coin? How often would I see a result this far from 50-50 by random chance? So first you might want to take a second and just think, what do you think? Is that enough? Is that a large enough departure that you would question the coin? Or does this seem like that realm of possibility with a fair coin? Okay, so let's go ahead and use hypothesis testing to answer this. And now we're going to use the normal distribution to answer this because we don't have, a countable number of categories, or well, I guess it's still countable with 100, but right, we don't have like 12 or 13 categories. Instead, we have 100. So that means that the distribution for p hat is now going to kind of approximate a normal distribution a little bit clearer. It's going to be a little bit more continuous looking. So we can just use normal distribution properties to calculate this a little fairly accurately. So the first thing that we're going to calculate is the standard error for p hat. So notice that our p hat value is, our p hat value is going to be 0.56. And our null hypothesis for p is going to be 0.5. So I'm going to write p naught, so p with a little 0 equals 0.5. So that's kind of like our null hypothesized value for this coin, that it's 50%. Now we've had 2 examples in a row with 50%. It doesn't have to be, but that's just the context of what we're studying here. And so the first question is, what is the standard error for p hat, given that we have a sample size of 100 coins? And also given that it should be 50-50, meaning that sigma would be 0.5 in this case. So then the standard error for p hat is going to be 0.5 divided by the square root of 100, which is just going to be 0.5 divided by 10, which is going to be 0.05. So that means that if we sample 100 coins like this, we would expect our p hat to be off by about 0.05 on average. Sometimes it will be less than that, sometimes it will be more than that, but that's kind of like the average amount of error we expect to see in p hat with a sample size of 100, because samples vary. We're not going to get exactly 50-50. We're going to have a little bit of error, and this quantifies that average or expected amount of error we should see with a sample size of 100 here. Now, if we increase that sample size, if we were looking at 1,000 coins, the standard error is going to go down. We're going to have a little bit less variation in the p-hats. It should be a little bit closer to 50% if we have more and more data to kind of converge around that true parameter. Now the next question, how many standard errors away from 0.5? How many standard errors away from 0.5 is our sample proportion of 0.56? So what I'm going to do is I'm just going to calculate this raw difference in the numerator and then divide by 0.05. So this is going to tell me how many standard errors away I am. And I'm going to get 0.06 as my distance. How many 0.05s away is that? Well, it's going to be about 1.2. That is 1.2 standard errors away from 0.5. So then my distribution of possible p-hats, should be centered at the true parameter of 0.5 if this point is fair. I observed a value of about 0.56, which is about 1.2 standard errors away. And I'm kind of asking this question of how unusual is this? And I can use the normal distribution to approximate how often I should see values this far or farther away. So basically, I'm looking for this area right over here. How often would I expect to get p-hats this far farther from 0.5 if it's really the parameter? However, this is a case that it might make more sense to actually calculate what's called a two-sided p-value or a non-directional p-value. And that's because the question we're really asking is how often should we expect to get a result this far away from 50-50? We don't actually care if it's in the positive or negative direction. We just care about this magnitude of difference. How often do we see a magnitude of difference of 0.56 or more in either direction? Or I should say of 0.06 or more in either direction. So this is a little bit different than the psychic example where I think it makes sense to do a one-sided p-value, right? We're only interested in the case where Milena is doing better than random chance. Now, if she got 3 out of 12, we're not going to be sitting here thinking, oh, is she psychic, right? That's not a question that crosses our mind. This is only unusual and interesting if she's on the higher end of this distribution. This, however, is not a case where it has to be one direction. It is just as unusual and interesting whether it be 56 heads or 56 tails. So I think it makes sense to think of this as a two-sided p-value where we're also finding the area where we get 44% or 44 or fewer heads as well. And this, by the way, should be about the same distance. I'm sorry if it doesn't quite look like the same distance, but it should be about the same amount of distance on either side. It should be symmetrical here. And we can use a function like p norm in R or a statistical table or something like that to find this probability using the normal distribution properties. So that's what I'm going to do here is I'm going to pull R back up, and I'm going to calculate, so this is going to be for the normal distribution probability. I'm going to use p norm, where my value is 0.56. My mean should be 0.5. My standard deviation for this distribution should be 0.05, because this is a sampling distribution, so we're going to use the standard error as our standard deviation here. And I'm looking for lower dot tail equals false if I want a one-sided p-value, because I'm getting the upper end of this curve. But if I want a two-sided p-value, I need to multiply it by 2. So I want this area this far above and higher, and then I'm going to multiply that probability by 2 to get the mirror side of that as well. So if I just did it by itself without the times 2, I just get the one-sided p-value. Multiplying it by 2 doubles that to get the other side as well. And I get 23%, which, as I'd kind of expect, isn't particularly unusual. So that means that my p-value equals 0.23, or we could also call it 23%. That means that 23% of the time we're going to see a p-hat of 0.06 or farther away from the true parameter here, given this information. So I don't know about you, but this seems like it's still in that realm of plausibility. It's obviously less than 50%, but this is like a 1 out of 4 situation. I don't think we really have any evidence to say the coin is unfair given this information because this is a perfectly normal result to see. So we would really want our p-value to be below 10% or more like below, I think, 5% or so before we really start to say we have some evidence that something is going on here and that maybe 50% isn't the true parameter going on here. A follow-up question for you, which I sort of mentioned a minute ago. If we had tossed this coin 1,000 times and still got 56% heads, would that affect our conclusion? Would the tail probability be the same or different? So feel free to pause and think about this because this is an important question. But I will go ahead and answer it here. Remember that the standard error in this case is going to go down as n increases, meaning that I should have more confidence in my sample statistic as a good estimate of the parameter when I have more data to construct it with. It also means that the distribution of my possible p-hats is going to get narrower and converge more clearly around p. So 0.56 might be more like over here now as opposed to kind of more in the center of this curve. And I just realized you can't quite see what I'm drawing there. So my distribution of possible p-hats will still be centered around 0.5, but it's going to be a lot narrower and a lot more focused. So just as we've talked about with sampling distributions before, it's going to converge around that true parameter when our sample size increases for each sample that we take. We're less likely to see sample statistics that are way over here. We're more likely to see sample statistics converging around the true parameter since we have large sample sizes. They should each be relatively good estimates of the parameter.